A bottleneck is any resource machine worker, work center, or step whose capacity limits the overall output of a production system, much like the narrow neck of a bottle that restricts how fast liquid can flow out. Classification: internal versus external. Internal bottlenecks exist inside the firm, for example, a CNC machine. External bottlenecks are outside the firm's control, for example, a supplier's lead time. Temporary versus chronic. Temporary bottlenecks appear due to maintenance breakdowns or seasonal spikes. Chronic bottlenecks persist over long periods because of inherent design or capacity constraints. Physical versus policy. A physical bottleneck is a machine with limited speed. A policy bottleneck is a rule like only one order can be released per day. Significance: identifying the bottleneck tells managers where to focus improvement efforts, because increasing capacity elsewhere will not raise total output until the bottleneck itself is alleviated. The classic highway analogy works well. Adding more lanes on a side road does not speed up traffic if the main bridge remains single lane. Understanding bottlenecks helps in 1. Setting realistic production goals. 2. Prioritizing investment, for example, buying a faster machine. 3. Designing schedules that keep the bottleneck operating at high utilization, while protecting other resources from excessive starvation or overload. Quantitative methods give objective evidence of where a bottleneck lives. 1. Utilization rates. Utilization equals actual output divided by design capacity times 100%. If a machine can produce 100 units per hour design but only makes 70 units per hour, its utilization is 70%. A high utilization close to 100% suggests the resource may be a bottleneck. 2. Throughput analysis. Throughput X is the rate of finished goods leaving the system units per hour. In a series line, the bottleneck's throughput equals the system's throughput because all other stations must wait for it. 3. Little's Law. L equals lambda times W. L equals average inventory or work in process at a station, lambda equals arrival rate units per hour, and W equals average time a unit spends their hours. Rearranged, W equals L divided by lambda. If W is unusually large at a station, it signals a bottleneck. 4. Process flow diagrams, PFDs. A PFD maps each operation, its cycle time, and the flow of material. By annotating each node with its cycle time Ct sub I and capacity C sub I equals 1 divided by Ct sub I, the smallest C sub I immediately spots the bottleneck. Visual cues, red highlighting of the longest time node, make communication easy. In practice, managers collect data: hourly output, downtime, queue lengths, compute utilization and throughput for every work center, then apply Little's Law to validate the suspected bottleneck. The minimum capacity theorem states that the overall throughput of a serial production system cannot exceed the capacity of its most restrictive resource, the bottleneck. X subsystem equals the minimum of C1, C2 through Cn, where Ci is the capacity units per hour of resource I. Derivation. Each resource I can produce at most Ci units per hour. For a unit to complete the whole process, it must pass through all resources. The slowest step determines the speed of the chain. Therefore, the system's maximum sustainable output X max equals the smallest Ci. Example: a toy-making line has 3 stations. Molding 120 units per hour. Painting 80 units per hour. Assembly 90 units per hour. The bottleneck is painting 80 units per hour. Even if we add more molding machines, the line cannot exceed 80 units per hour unless we increase painting capacity. Implication: when planning expansions, the rule of thumb is to first raise the bottleneck's capacity. Otherwise, extra capacity elsewhere remains idle, driving up cost without improving output. Capacity planning is organized into 3 decision-making layers, each with its own time horizon and focus. Strategic: 3 to 5 years or more. Typical decisions: build new plants, purchase major equipment, outsource versus insource, location choice. Example: deciding to construct a second factory in Mexico to serve Latin America. Tactical: 6 to 24 months. Adjust workforce size, add a shift, lease temporary equipment, negotiate supply contracts. Example: adding a 3rd weekend shift on the bottleneck machine to increase capacity by 30%. Operational, daily to weekly. Schedule jobs, release work orders, assign operators, manage preventive maintenance. Example, issuing daily work order releases that subordinate all other stations to the bottleneck's pace. Decision-making logic. Strategic choices set the design capacity, the maximum possible output. Tactical decisions shape the effective capacity, what is realistically achievable given policies, labor, and maintenance. Operational decisions aim to keep the bottleneck fully utilized while smoothing variability, for example using buffers. The hierarchy ensures that short-term actions, operational, are consistent with medium-term plans, tactical and long-term objectives, strategic. Design capacity, DC- the theoretical maximum output under ideal conditions, no downtime, perfect quality. Example, a press that can run 200 cycles per hour. Effective capacity, EC- the realistic maximum after accounting for planned downtime, maintenance setup, and quality loss. Effective capacity equals design capacity times 1 minus planned downtime percent times 1 minus quality loss percent. Utilization U- how much of the design capacity is actually used. Utilization equals actual output divided by design capacity times 100%. Efficiency E- how well the effective capacity is used. Efficiency equals actual output divided by effective capacity times 100%. Variability adjustments - unplanned variability breakdowns, urgent orders reduces effective capacity. A common adjustment is the capacity cushion. Adjusted effective capacity equals effective capacity times 1 minus variability cushion percent. Practical example. Design capacity equals 200 units per hour. Planned downtime equals 10% maintenance breaks. Quality loss equals 5%. Variability cushion equals 8% for breakdowns. Then, effective capacity equals 200 times 1 minus 0.1 times 1 minus 0.05 equals 200 times 0.9 times 0.95 equals 171 units per hour. Adjusted effective capacity equals 171 times 1 minus 0.08 equals 157.3 units per hour. If the actual output is 150 units per hour, utilization equals 150 divided by 200 equals 75%, and efficiency equals 150 divided by 171 equals 87.7%. These numbers tell managers that the resource is well efficient, but not fully utilized. Perhaps the bottleneck lies elsewhere. Explanation. Rough Cut Capacity Planning, RCCP, bridges the high-level Master Production Schedule, MPS, and detailed shop floor schedules. It answers the question, can we meet the MPS with the available capacity? Step-by-step RCCP. Step 1. Translate MPS into required capacity per work center. Multiply each MPS quantity by the routing time, hours per unit, for every operation. Step 2. Determine available capacity. For each work center, compute a C equals DC times available shifts times hours per shift times 1 minus planned downtime. Step 3. Compute load ratio. LR equals required capacity divided by available capacity. LR greater than 1 indicates a capacity overload. Step 4. Identify overloaded centers. Those with the highest LR become the immediate bottlenecks. Step 5. Adjust the plan. Options: add overtime, add a shift, outsource, or revise the MPS. Step 6. Iterate until all LR less than or equal to 1, or within an acceptable cushion, for example, 85 to 90%. Sample calculation. MPS Week 1 demand equals 1,200 units of Product A. Routing for Product A. Cutting 0.4 hours per unit. Welding 0.6 hours per unit. Painting 0.3 hours per unit. Work center capacities DC. Cutting 200 hours per week. Welding 240 hours per week. Painting 180 hours per week. Required capacity. Cutting 1,200 times 0.4 equals 480 hours. Load ratio equals 480 divided by 200 equals 2.40, overload. Welding 1,200 times 0.6 equals 720 hours. Load ratio equals 720 divided by 240 equals 3.00, overload. Painting 1200 times 0.3 equals 360 hours. Load ratio equals 360 divided by 180 equals 2.00, overload. All centers are overloaded. The highest LR is welding 3.0. Action, add a second welding shift, extra 240 hours. New available capacity for welding equals 480 hours. Load ratio equals 720 divided by 480 equals 1.5, still high. Consider outsourcing welding for 300 hours, reducing required welding capacity to 420 hours. Load ratio equals 420 divided by 480 equals 0.875, acceptable. RCCP thus provides a quick rough cut view before detailed scheduling. Explanation: queuing theory models the waiting line that forms at a bottleneck. Two common single server models are M/M/1, Markovian arrivals in service, and M/D/1, Markovian arrivals, deterministic service. M/M/1 model. Arrival rate lambda units per hour. Service rate mu units per hour. Traffic intensity rho equals lambda divided by mu. It must be less than 1 for stability. Key results: average number in system, Q plus service, L equals rho divided by 1 minus rho. Average time in system, W equals 1 divided by mu minus lambda. Average number in Q, L sub Q equals rho squared divided by 1 minus rho. Average waiting time in Q, W sub Q equals lambda divided by mu times mu minus lambda. Derivation of W. Using Little's law, L equals lambda times W, and the expression for L above, solve for W equals L divided by lambda, which equals 1 divided by mu minus lambda. M/D/1 model, service time constant equals 1 divided by mu. Same lambda and mu, but reduced variability lowers waiting. Average number in system, L equals rho plus rho squared divided by 2 times 1 minus rho. Average time in system, W equals L divided by lambda. Average waiting time in Q, W sub Q equals rho divided by 2 times mu times 1 minus rho. Example: a bottleneck machine processes 30 parts per hour, mu equals 30. Parts arrive at 24 per hour, lambda equals 24. Rho equals 0.8. M/M/1. W equals 1 divided by 30 minus 24, which is 1/6 hour, about 10 minutes. L equals 0.8 divided by 0.2, which is 4 parts in system. M/D/1. W sub Q equals 0.8 divided by 2 times 30 times 0.2, which is 0.0667 hour, about 4 minutes, showing deterministic service halves the wait. These formulas let managers quantify how severe the bottleneck's queue will become and compare alternatives. For example, adding a parallel machine. When a bottleneck is identified, managers have several strategic levers to improve overall throughput. Subordination: align all other resources to the bottleneck's pace. Low cost, easy to implement, works when bottleneck capacity cannot be quickly increased. No extra capital, reduces work in process and inventory holding costs. Elevation: directly increase bottleneck capacity by adding a machine, extra shift, or faster tool. High impact, justified if return on investment is greater than the required hurdle, for example 12% annual. Additional cost equals purchase price plus operating cost. Benefit equals extra units times contribution margin. Buffer allocation: insert time or inventory buffers before or after the bottleneck to absorb variability. Useful when variability is high and extra capacity is expensive. Buffer cost equals inventory carrying cost. Benefit equals lower stock outs and smoother flow. Process redesign: change the routing to bypass, parallelize, or simplify the bottleneck operation. Viable if redesign does not compromise quality. Cost equals engineering time. Benefit equals permanent capacity lift without new equipment. Technology upgrades: adopt automation, artificial intelligence scheduling, or faster tooling. High upfront cost, justified when long-term demand growth is forecasted. Payback period equals upgrade cost divided by annual incremental profit. Example decision framework. Calculate bottleneck contribution margin. CM equals selling price minus variable cost. Estimate incremental profit from each option. Delta profit equals delta capacity times CM minus additional cost. Rank options by delta profit divided by investment, also known as return on investment. Select the highest return on investment that meets strategic risk tolerance. By systematically applying this framework, managers avoid ad hoc fixes and ensure that every dollar spent truly moves the bottleneck forward. Question 1 Bottleneck detection. A 3-stage line produces 500 units per day. Data collected for a typical day. Stage 1 8 hours available, 1,000 minutes total processing time. Stage 2 8 hours available, 1,150 minutes total processing time. Stage 3 8 hours available, 900 minutes total processing time. Identify the bottleneck and compute its utilization. A solution. Convert minutes to hours: stage 1 equals 1,000 divided by 60 equals 16.67 hours. Stage 2 equals 1,150 divided by 60 equals 19.17 hours. Stage 3 equals 900 divided by 60 equals 15 hours. Compute utilization equals processing time divided by available time. U1 equals 16.67 divided by 8 equals 2.08, which is greater than 100%, meaning overtime or backlog. U2 equals 19.17 divided by 8 equals 2.39, which is greater than 100%. U3 equals 15 divided by 8 equals 1.88, which is greater than 100%. The highest utilization is stage 2, 2.39, thus stage 2 is the bottleneck. If capacities were expressed as units per hour, the same conclusion follows. Question 2 Capacity variance. A CNC machine designed capacity 120 units per hour has planned downtime of 5% and a quality loss of 3%. Unplanned breakdowns are expected 4% of the time. Calculate a effective capacity, B adjusted effective capacity. See utilization if the machine actually produces 90 units per hour. A solution. Part A effective capacity equals 120 times open parenthesis 1 minus 0.0, 5 close parenthesis times open parenthesis 1 minus 0.03 close parenthesis equals 120 times 0.95 times 0.97 equals 110.46 units per hour. Part B variability cushion equals 0.04. Adjusted effective capacity equals 110.46 times open parenthesis 1 minus 0.04 close parenthesis equals 106.04 units per hour. Part C utilization versus design equals 90 divided by 120 equals 0.75, or 75%. Efficiency versus effective equals 90 divided by 110.46 equals 0.815, or 81.5%. Question 3 RCCP and resource allocation. Master production schedule for next week 800 units of product X. Routing hours per unit: cutting 0.25, machining 0.45, finishing 0.20. Weekly capacities: cutting 150 hours, machining 300 hours, finishing 140 hours. Determine if the plan is feasible and propose a corrective action. A solution. Required capacity. Cutting equals 800 times 0.25 equals 200 hours. Load ratio equals 200 divided by 150 equals 1.33, overload. Machining equals 800 times 0.45 equals 360 hours. Load ratio equals 360 divided by 300 equals 1.20, overload. Finishing equals 800 times 0.20 equals 160 hours. Load ratio equals 160 divided by 140 equals 1.14, overload. All centers overloaded. Cutting is most critical with load ratio 1.33. Corrective action: add a second cutting shift providing an extra 150 hours. New cutting capacity equals 300 hours. Load ratio equals 200 divided by 300 equals 0.67, acceptable. Machining still overloaded. Consider outsourcing 100 hours of machining or add overtime to reduce load ratio to less than or equal to 0.90. Question 4. Queuing at a bottleneck. A bottleneck workstation has mu equals 25 units per hour. The arrival rate is lambda equals 20 units per hour. Calculate an average number of units in the system M1. B. Average waiting time in queue. See the effect on waiting time if service time becomes deterministic MD1. A solution. Rho equals lambda divided by mu equals 20 divided by 25 equals 0.8. Part A MM1L equals rho divided by open parenthesis 1 minus rho close parenthesis equals 0.8 divided by 0.2 equals 4 units. Part B W sub Q equals rho divided by open parenthesis mu times open parenthesis 1 minus rho close parenthesis equals 0.8 divided by 25 times 0.2 equals 0.16 hour, which is 9.6 minutes. Part C MD 1 waiting time in queue equals rho divided by open parenthesis 2 times mu times open parenthesis 1 minus rho close parenthesis equals 0.8 divided by 2 times 25 times 0.2 equals 0.08 hour, which is 4.8 minutes. Deterministic service halves the waiting time, illustrating the benefit of reducing variability. These problems test the student's ability to locate the bottleneck, adjust capacity for variability, apply RCCP, and use queuing formulas, core competencies for operations management MBA programs.